Some things in the world really are just black and white, right? Like PC or Mac, Coke or Pepsi, boy or girl, analog or digital. Yeah, there can't really be any in between, can there? This is true in powering our designs as well. We typically either choose analog power with limited flexibility but lower cost and simpler components, or we choose digital power, which is incredibly sophisticated and flexible, but more expensive and more complex to design in. But what if there was an in-between gray area for power design that gave us some of the best of both worlds? Hi, I'm Amelia Dalton, host of Chalk Talk. Today, my guest is Steve Stella from Microchip, and we're going to talk about a gray area most of us didn't know about: digitally enhanced analog power control. It's true, and it's cool, and we're going to talk about it right now. Before we get started, I want to remind everyone that you can click on that Download Now button below your player. There you can download a free white paper that further expands on this topic. Hi, Steve. Thanks so much for joining me today.
Thanks, Amelia. It's a pleasure to join you.
So I'm trying to wrap my head around this digitally enhanced analog idea. What the heck does that mean?
A little confusing, isn't it?
It is.
It's a very common question, and it's probably best to take a step back and look at the fundamental control technologies. So this digitally enhanced power analog is really focused on power conversion devices.
Okay.
And so what we're looking at is digital control techniques and analog control techniques. These are very, very common. Everyone should know them.
Sure.
But just to make sure we are on the same page, when I say digital control, I mean that everything is controlled in the digital domain. So your control variables are converted into digital and modified in the digital domain, and then those drives your power conversion loop.
Sure.
Now on the analog side, we don't do that digitization. Everything is maintained in the analog loop.
Yeah.
We live in an analog world, so it's pretty easy, pretty straightforward.
Okay, so Steve, I think I'm familiar with both of these techniques, but you said we were going to mix them together somehow. How does that happen?
No, exactly true. So each of these digital and analog techniques have trade-offs, right? They have
Sure.
their benefits, they have their trade-offs.
Uh-huh.
So how we think about it is in terms of a power conversion space. We don't think about it in terms of just analog or just digital. We want to combine those two together, and that's what we're able to accomplish with hybrid control. So you've probably heard of hybrid control, mixed signal control, which is a combination of analog and digital.
Yeah.
And so what we've done is build on that concept of hybrid control by introducing this digitally enhanced power analog. So digitally enhanced power analog, I know sounds confusing, has
Yeah.
both digital, has both analog. What the heck are we talking about? It's hybrid control, mixed mode control.
Okay.
And so what we do is we take those various control techniques, the digital control or the analog control, and we actually morph them together,
Okay.
trying to maintain the advantages of both and providing you with new ways of doing things, new opportunities, new flexibilities for your applications.
Very cool. Okay. So I think I get how this hybrid control works, but why would we want to do that?
Oh, yeah, that's a very common question. And really, if we think about it in terms of digital is very flexible.
Yeah.
Digital, very expensive.
Yes.
Analog, it's very good at what it does, but it does that one thing
Right.
really, really well.
Yeah.
So what we do when we combine the two together is really have the cost-effective performance of the analog solution, get the performance of the analog solution, but we still maintain some of the flexibility of a digital solution. So we're able to combine those together to improve the overall solution.
Very cool. Okay. So, Steve, this seems like something I could already do with discrete parts from Microchip. Why is this different?
You can do it to a certain degree.
Okay.
So there is a discrete implementation, and the discrete implementation provides you with a great deal of flexibility in terms of selecting your components, sizing it to your application, and
Right.
achieving the results that you're looking for. Unfortunately, what you really need in order to fully leverage analog control, fully leverage flexibility in analog control, is being able to interface that microcontroller more closely with the analog controller.
Right.
And in a discrete implementation, that's very difficult. You need a dedicated microcontroller, you need a dedicated analog controller. I hear dollar signs,
Yeah,
which
no,
is
thank
good for
you.
me as a marketing guy, probably not what you're looking for.
No.
But we have developed a technology that allows us to combine those two together into a single process cost effectively.
Yes.
So now we're able to integrate a microcontroller with the analog controller and even some other mid-voltage components, including MOSFET drivers and LDOs, so that we combine a fully functional, very flexible analog-based control solution with that digital interface.
Very cool. So I'm definitely in favor of integration as a whole. Less stuff on my board, smaller bill of materials.
You're exactly right. And that's what the technology enables. So it's the performance and functionality that we're trying to get from a complete solution, maintaining the performance of the analog power conversion. That technology incorporates the flexibility of a digital solution, and then we get to integrate, which allows us to provide some very unique and interesting solutions for your types of applications.
Cool. This is great, Steve. What kind of cool things can we do with this?
Unsurprisingly, with the flexibility of the device, you can do a whole bunch.
Sweet.
So depending on what your current application, what your current project is, you can do power supplies and typical point of load applications.
Okay, yeah.
Don't need any additional components for 12-volt rail conversion to core voltages.
Very nice.
LED drivers, this technology can be converted into a current source as well, so you can control those currents very well.
Okay.
And that's useful in both automotive and commercial lighting type applications, so it's a very broad market space. Battery chargers, very similar to LED drivers. You're driving currents, you're driving voltages.
Right.
The flexibility of that digital interface allows you to modify the behavior of that analog controller to charge any type of multi-chemistry cells.
Okay, yeah.
So depending on your application, instead of programming in the analog domain with resistors, capacitors, setting set points for current limits, voltages,
Right.
you can now just update tables in the microcontroller to get the voltage set points, current set points, and really makes it easy to design battery chargers. And then there's multi-rail power supply applications as well, so these can be combined together. There's master-slave modes that allow them to communicate with each other so that you're able to manage the input power as well.
Gotcha, okay.
So maybe it's best if we look at an example.
Sure.
So let's say your analog power supply design is working well,
Yeah.
and then customer or application needs change.
Wait a second, Steve. My application needs never change.
Well, that just means that you're too good then.
Right, okay.
But for the rest of us mortals, it's very common that customer application needs change.
That's true, okay.
And maybe they need higher system efficiencies at a particular operating point. Perhaps their loads have changed. Or maybe their customers need some kind of communication.
Sure.
Right? They want to know what this power supply is doing. How much is their load consuming? Is there a problem with their load? And this is valuable information. Does it make more sense for the power supply to do that, or does your customer need to add some external capability, which is always cost and headache for them?
Yep, Steve, I can see that stuff happens a lot. But what do we do about it?
And that's the question. Of course, if you have a digital power supply, there are options. You change a few pieces of code, and you can alter the performance of the supply to get the performance that you're looking for. And of course, communication is pretty easy with a digital power supply.
Yeah.
Certainly much fewer options with today's analog designs. So do you add an external digital interface? That's great for monitoring and perhaps some communication, but it's a one-way, right? You're only going to take information from the analog power supply, and you're going to return it to whomever is looking for it.
Right.
You can't really change anything. So there are some challenges then with the analog supply.
So, Steve, if we started off with analog, we're kind of have a bit of a problem, right?
In the past.
That's
right.
okay.
That's right. So really the question then is, do you go digital?
Yeah.
That's a pretty big step because it's not a simple or easy or straightforward conversion to go from analog to digital. It requires a new set of expertise. It requires software engineers. And for a lot of analog type companies, software engineers are not necessarily sitting around doing nothing.
Right.
Of course, then software tools can't do anything without tools. So you need to invest in a significant tool set, and then they need to know which tool set you've provided them.
Right.
Done training every now and again. You need to be able to control that software process, so it adds a great deal of complexity in the digital power.
I can see that. So, Steve, you're a marketing guy. I bet you're going to tell me there's a better option.
Of course I'm going to tell you that there's a better option. As an intermediate step, this digitally enhanced power analog provides, as we've talked about, the performance of the analog converter with some of the flexibility of a digital converter so that you have that communication interface and then you can modify the behaviors to address the changes in customer requirements.
Very cool.
Again, just kind of summarizing, on the analog power conversion side, you don't need that high-performance microcontroller to do all of your digital manipulation. You don't need a high-precision, high-speed analog-to-digital converter to digitize the analog signals. That saves a lot of cost and a lot of power since you're not running those peripherals.
Sure.
Of course, on the digital side, now you don't need the digital control expertise. So you don't need to hire a new digital workforce to address your digital power conversion design. What we're able to do is use a small integrated MCU which actively optimizes that analog control loop. It's much simpler than digital control because, again, we maintain in the analog domain. But it does allow for advanced features like the configurable analog, which is new and unique, and then a communication interface, of course, and it is a fully programmable MCU. And what that allows is some custom IP to be incorporated into this design as well.
Ah, right. Okay. So, Steve, this is a great concept, but do these really exist? I mean, and I guess if so, let's get down to some specifics about these parts.
I'm more than happy to talk about specifics. So Microchip has launched a first in family, the MCP19111, which is our first digitally enhanced power analog controller. It is a single-phase synchronous buck device, which operates over a very wide input voltage, 4.5 to 32 volts. This makes it ideal for 5, 12, and 24 volt rails.
Right.
Work on those every now and again?
Every now and again.
Of course, then there's the programmable analog controller, which offers a lot of flexibility in just the behavior of the analog. And then thresholds can be set as well. So depending on your application, you can reset your UVLO, your current limits. Again, I just want to stress the flexibility for your applications. And then it has an internal analog to digital converter, so it is capable of measuring internal signals to the device, like input voltage, output voltage, and temperature. But there's also a GPIO, general purpose IO, that allows external signals to be brought in and measured and then communicated over a communication interface. So we get to the digital core. That's where the communication interface, I2C, pretty standard. And then it does have 4K words of flash and 256 bytes of RAM. So it's a small but capable microcontroller. Then the process that we've developed also allows us to integrate, as we've talked about, some mid-voltage components like the LDO and MOSFET drivers.
Very cool. Okay, Steve, I'm ready to get started. What do I need to use one of these things?
Easiest to go to our website,
Okay.
www.microchip.com/MCP19111.
All right.
And there you will find a lot of development tools. So we have software tools that allow us to help you specify the register settings within our device. This allows you to calibrate the device, to stabilize the device for your application.
Nice.
And then there's also a graphical user interface that we provide just to help simplify the interaction between programming and the configuration so that you don't need to code. Are you a good software engineer?
Let's not talk about that.
Okay, so you'll find the graphical user interface very helpful in getting you up and running very quickly. And then that works with the hardware tools, the evaluation board, that really allows a customizable platform to help you develop your application.
Fantastic.
And that really summarizes it for us. That's your introduction to digitally enhanced power analog, where you're able to enjoy the performance of analog with the flexibility and configurability of digital.
All right. Well, I think that's all I have time for today. Thank you so much for joining me today, Steve. It was really cool learning about this.
Thank you, Amelia, and good luck on your project.
Thanks. And before we go, don't forget to click that Download Now button below the player to download a free white paper that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.